Hello, and welcome to Pro Knowledge Station.
We will study Parseval's theorem in Fourier analysis. We will build intuition, explore the Fourier series and Fourier transform forms, and walk through a clean step-by-step proof. Let's begin with the big idea. Parseval's theorem says the total energy of a signal in the time domain equals the total energy of the same signal in the frequency domain. Let's visualize what that means with two bars representing energy. Think of a signal as a function of time. The energy is the integral of the squared magnitude. In the frequency domain, the energy is the integral of the squared magnitude of its Fourier transform. Parseval tells us these are equal. Now, let's state the Fourier series context. For a periodic signal f of t with period t, we can write it as a sum of complex exponentials. The coefficient c sub n captures the strength of each harmonic. Parseval's theorem for Fourier series states that the average power of the periodic signal over one period equals the sum of the squared magnitudes of the Fourier coefficients. For the real trigonometric form, the signal is written with cosine and sine coefficients. Parseval's identity becomes a clean sum of squares of the a sub n and b sub n coefficients. For non-periodic signals, we use the Fourier transform. Parseval's theorem becomes an energy conservation formula, also called Plancherel's theorem. Let's outline a proof for the Fourier transform version. We start with the energy in the time domain, then we substitute the inverse transform, swap the order of integration, and recognize the Fourier transform. The result is the energy conservation formula. In physics and engineering, Parseval's theorem means total energy is preserved when we transform signals. In signal processing, we can measure power either by time samples or frequency components and get the same answer. In applied math, it also helps evaluate infinite series and analyze orthogonal functions. Let's summarize. Parseval's theorem states that the energy of a signal in the time domain equals the energy in the frequency domain. This works for Fourier series and Fourier transforms. It connects time, frequency, and energy in a beautiful, powerful identity. We will solve a classic Fourier series problem using Parseval's theorem. We'll go step by step, connect the algebra to the geometry, and compute two infinite series exactly. Here is the given Fourier series. We are told that for x between minus pi and pi, the function x squared has the Fourier series x squared equals pi squared over 3 plus 4 times the sum from n equals 1 to infinity of negative 1 to the n over n squared times cosine of nx. We will use Parseval's theorem to evaluate the sum of 1 over n to the fourth, and then use that result to compute the alternating series with negative 1 to the n over n to the fourth. First, let's visualize what this series represents. On the interval from minus pi to pi, the function is the parabola y equals x squared. The Fourier series extends this shape periodically. Now, let's recall Parseval's theorem. If a function has Fourier series coefficients a(n) and b(n) on minus pi to pi, then the average value of the square of the function equals the sum of the squares of the coefficients. Specifically, 1 over pi times the integral from minus pi to pi of f of x squared equals a 0 squared over 2 plus the sum from n equals 1 to infinity of a n squared plus bn squared. In our case, f of x is x squared. The given series already tells us the coefficients. Notice the series has only cosine terms, so all bn are 0. Compare the given series to the standard cosine expansion, and we can read off a 0 and an directly. Now, we compute the left side of Parseval. We need the integral of x to the fourth, because f of x squared is x to the fourth. Let's compute 1 over pi times the integral from minus pi to pi of x to the fourth. Since the function is even, we can double the integral from 0 to pi. Now, we compute the right side of Parseval. We have a 0 equals 2 pi squared over 3, so a 0 squared over 2 equals 2 pi to the fourth over 9. And a n equals 4 times negative 1 to the n over n squared. So a n squared equals 16 over n to the fourth. Now put it all together. Now solve for the sum. Subtract 2 pi to the fourth over 9 from both sides, then divide by 16. Great. Now we use this to compute the alternating series with negative 1 to the n over n to the fourth. The sign alternates. Odd terms are negative and even terms are positive. We can separate the even and odd parts. Let's compute the even part first. Even terms have n equals 2k, so the even sum is 1 over 16 times the full sum. Then the odd sum is the full sum minus the even sum. Finally, we combine them to get the alternating sum. So the alternating series is negative 7 pi to the fourth over 720. Let's summarize the key results. We used Parseval's theorem on the Fourier series of x squared to compute a beautiful zeta value. First, the sum of 1 over n to the fourth is pi to the fourth over 90. Second, the alternating version is negative 7 pi to the fourth over 720. These results show how Fourier analysis turns a trigonometric series into an exact evaluation of an infinite sum. Thanks for watching. If you'd like, we can also derive the Fourier series of x squared from scratch, or explore Parseval's theorem for other functions. We will solve a classic Fourier analysis problem using Parseval's theorem. We will compute the Fourier series of a square wave, prove a famous sum of reciprocal odd squares, and then find how much power is in the first few harmonics. First, let's write the square wave. We consider a periodic function with period 2 pi. It takes the value a on the interval from 0 to pi and negative a from negative pi to 0. This function is odd and symmetric about the origin. Let's visualize one period of this square wave. The function jumps up to a for the positive half and down to negative a for the negative half. We'll use a equals 1 just for the picture. Now we compute the Fourier series. Because the square wave is odd, only sine terms remain. The general series becomes a sum of b sub n times sine of nx. So our task is to find the b sub n coefficients. For an odd function, b sub n equals 2 over pi times the integral from 0 to pi of f of x times sine of nx. Since f of x equals a on that interval, we get a simple integral. This produces the classic result that b sub n equals 4a over n pi for odd n and 0 for even n. So the Fourier series becomes a times a sum of only odd sine terms. We can write it as 4a over pi times sine, x plus 1/3 sine, 3x plus 1/5 sine 5x, and so on. Now, we apply Parseval's theorem. It says that the average of the square of the function equals the sum of the squares of the Fourier coefficients for a 2 pi periodic function. The formula is 1 over pi times the integral of f squared equals a sub 0 squared over 2, plus the sum of a sub n squared plus b sub n squared. For our square wave, a sub 0 and all a sub n are 0 since the function is odd. The left side becomes 1 over pi times the integral of a squared over the interval from negative pi to pi, which gives 2a squared. The right side becomes the sum of b sub n squared for odd n. Substituting b sub n equals 4a over n pi, we obtain a sum of reciprocal odd squares. This gives pi squared over 8 equals 1 plus 1 over 3 squared plus 1 over 5 squared, and so on. Next, we interpret this in terms of power. The average power in a periodic signal is the average of f squared. For our square wave, that is a squared. Each harmonic is a sine wave with amplitude 4a over n pi, so each harmonic contributes power equal to 1/2 times that amplitude squared. The fraction of power in the first harmonic is the power at n equals 1 divided by total power. This equals 8 over pi squared, which is about 0.81. So roughly 81% of the power is in the first harmonic. Now let's include the first 3 odd harmonics, n equals 1, 3, and 5. The power fraction becomes 8 over pi squared times the sum of 1 plus 1 over 9 plus 1 over 25. This is approximately 0.93 or 93%. Finally, how many harmonics are needed to reach at least 95% of the total power? We compute partial sums of the odd reciprocal squares. If we include n equals 1, 3, 5, and 7, the sum is 1 plus 1 over 9 plus 1 over 25 plus 1 over 49. Multiplying by 8 over pi squared gives about 0.95. So we need the first 4 odd harmonics, up to the 7th harmonic. To summarize, we built the Fourier series of the square wave, used Parseval's theorem to derive the odd reciprocal sum, and used the harmonic coefficients to compute energy fractions. This connects pure Fourier theory directly to real signal power distribution. We solve a boundary value problem using Fourier series, and then apply Parseval's theorem to compute the integral of y squared from 0 to pi without explicitly writing y of x. We will go slowly and step by step. Here is the boundary value problem. we have y double prime plus lambda y equals f of x on the interval 0 to pi. The boundary conditions are y of 0 equals 0 and y of pi equals 0. We are given f of x equals x times pi minus x. We will represent f using a sine Fourier series, solve for the sine series of y, and then apply Parseval's theorem to compute the integral of y squared from 0 to pi. Finally, we will discuss how the result depends on lambda, because the boundary conditions force y to be 0 at x equals 0 and at x equals pi. The natural eigenfunctions are sine functions. That means we expand f of x and y of x in a sine series. Sines automatically satisfy the same 0 boundary conditions. We write f of x as a sine series. The formula is f of x equals the sum from n equals 1 to infinity of b sub n times sine nx. The coefficients b sub n are given by 2 over pi times the integral from 0 to pi of f of x times sine nx. Now we compute b sub n for f of x equals x times pi minus x. We will set up the integral carefully, then simplify it. We will not do every integration detail on screen, but we will show the clean result. After integration by parts, the coefficient simplifies nicely. The result is b sub n equals 4 times 1 minus negative 1 to the n, all divided by n cubed. This means only odd n contribute, because 1 minus negative 1 to the n is 0 when n is even. Next, we expand y of x in the same sign basis. Y of x equals the sum of a sub n times sine, nx. We substitute into the differential equation and use orthogonality to get a clean relation for each coefficient. Differentiate term by term. Y double prime is the sum of negative n squared a sub n sine, and x. Substituting into the equation gives negative n squared a sub n plus lambda a sub n equals b sub n for each n. So a sub n equals b sub n divided by lambda minus n squared. So the Fourier representation of y is y of x equals the sum of b sub n over lambda minus n squared times sine nx. This is the solution in series form. Now we use Parseval's theorem for sine series. If y of x equals the sum of a sub n sine nx, then the integral from 0 to pi of y squared equals pi over 2 times the sum of a sub n squared. We already found a sub n equals b sub n over lambda minus n squared. So we substitute into Parseval. That gives the integral equals pi over 2 times the sum of b sub n squared over lambda minus n squared quantity squared. Now plug in the explicit coefficient formula for b sub n. Remember b sub n equals 4 times 1 minus negative 1 to the n over n cubed. So b sub n squared becomes 16 times 1 minus negative 1 to the n squared over n to the sixth. Since 1 minus negative 1 to the n is 0 for even n, the sum reduces to odd n only. So the final Parseval expression is a clean odd n series. The integral equals pi over 2 times the sum over odd n of 64 over n to the sixth divided by lambda minus n squared quantity squared. We can write n equals 2k minus 1 to emphasize odd terms. Now, let's discuss how the result depends on lambda. Look at the denominator, lambda minus n squared. If lambda equals n squared for some integer n, the coefficients blow up, meaning the boundary value problem hits resonance. And the solution is not finite unless the corresponding b sub n is 0. Because b sub n is non-zero for odd n, any lambda equal to an odd square will cause a divergence. If lambda is far from every n squared, the denominators are large and the integral becomes smaller. So the integral is a smooth function of lambda except at eigenvalues n squared, with strong spikes near odd squares.
Don't forget to like this video, share it with your friends, and subscribe to Knowledge Station. Thank you for watching.